hope you are curious on that topic. So, first of all, a question: who attended this talk today in the morning? Okay, just fine. Okay, so basically it was not the worst idea to do it twice because it's pretty crowded. So I'm going to talk about performance. Not about how to earn a Porsche by coding JavaScript, but how to do quick programming in the web. I just fixed my slides because I realized that I have no single cat in my slide deck. So now we have a cat. My name is Sebastian. I'm from Munich. I work at a company named MaibornWolff, which does fancy things in the web, mainly for big customers which do cool things in the web, such as running power plants with web technologies and coal and stuff, and driving cars and so on. So pretty interesting stuff. And yeah, I'm focusing on doing those things with JavaScript. Once I gave a talk and I told the people who wants to run a power plant with JavaScript gets a day of consulting for free. And sadly, there were some people who actually tried that. And they're still alive, so no panic. But that kind of things. So I have GitHub and Twitter and stuff like that. So, but now to the main topic. Hopefully the thing does not break. How to speed up your application. Why is this interesting for us? Because of two reasons. First of all, there is Google, and Google does not like slow pages. If your application or your web page or everything in the web is slow, then Google says, no, you can do it better, and until that, you're going to be ranked down. So if you want Google to put you up in the index, you better have to be fast and you deliver the right content. The second reason why we have to build fast applications is because of your users. Most of the internet users don't like to wait. And I'm a typical internet user and I don't like to wait for pages. The worst thing you can do to me is present me a white page for a second or two and then I'm off. And I'm going to some competing company and buy their stuff. So it's all about speed and all about keeping your customers. So who does optimizations in JavaScript code or in web in general? Oh, and the rest of us does not care about performance at all. Okay, we have to talk afterwards. Seriously. Okay. What's the difference? This is code. And there is something about caching values. And the first one is not cached and the second one is cached. So far for the hints. The length of the array. Yes. And why do I've got an upgrade. This one here. Why do I do this? You don't have to query the value every time. You just store it once and then use it. Absolutely correct. So in this one, I go to my array object and ask it, how long are you? And this is done for every iteration over this loop here. So I'm gaining 0.1 millisecond by this operation. And if you imagine an application with a couple of 10,000 or 100,000 lines of JavaScript code, this does not make your code more readable. So far, so good. So remember those numbers. Less than 0.1 milliseconds. So what does your engine do? Okay, we just rearranged something and we are just iterating over the same structure. And you can see here, the first one is around 1.7 milliseconds, and the second one is 0.079, which is a little bit more of a performance gain compared to the first one. So the point is, optimizing your JavaScript code is not your problem. You don't want to gain less than 0.1 millisecond. Seriously. Because in exchange you get unreadable code, so just forget about that. The important thing is you have to know your environment, you have to know how your engine, your browser works, and what stuff your browser does to your source code in order to display it. And that's the main thing. So don't go over your code and cache some weird variables because it's just gaining some fractions of a millisecond, because that's relatively pointless. Have a look at your application, find where your pain points are and fix them, not some micro optimizations in your code. Yeah, that's funny and you can do it, but not all the time. What's interesting for Google and for us? It's the time between the point where the user hits in the URL, submits, and gets the response back, or the page rendered in the browser. Luckily, there is a term for this time period and the process that's running in that time in the browser. So you can Google or Stack Overflow it. It's named the critical rendering path. And this critical rendering path is the time span between receiving all the stuff from your web server and rendering the information for the user, so your user can interact with your page. And that's important because that's the key of getting your user in touch with your application. So if the time's too long between this one here and that, you lost. And the problem is between this view and that, the browser has to do a lot of work. And you can help the browser to do his work when you know what the browser does and how you can improve the process. So what does your browser have to do? First of all, the browser needs HTML. Then the browser needs CSS. Then all the things get merged together into a thing called render tree, and then the stuff is rendered on the screen. Fine. Who does not know these principles or didn't have to do anything with the DOM, CSS, OM, or render tree? So everybody can explain what the process between the raw HTML structure and the DOM is. No? Okay, fine. Because I've prepared something, luckily. So if there is an expert here who can explain this, I'll shut up and hand over the microphone. For everyone else, first of all, our browser, our client, and our server are machines, and they are communicating with bits and bytes. So the first representation of your web application or web page is a stream of bytes. If you present this to your user will simply walk away. Then your browser needs to get the structure out of this byte stream. and transform it into some characters, which is plain text. Fine. As soon as we have this plain text, our browser interprets this plain text and applies some rules. And these rules are defined by the W3 org, and this is the HTML standard. And this character string is transformed into a set of tokens. And these tokens are simply the HTML tags and the content of these tags. Out of these tokens, nodes are created. Nodes are the logical representation of the single nodes of your web application. And out of these nodes, a tree is formed. And that's simply because tree structures can be processed more efficiently than some bunch of nodes. So at the end, we have a structure tree of our web application named DOM, the Document Object Model. And that's the structure we interact with our JavaScript. So if you want to insert a new element in your page, you go into that DOM and insert somewhere a new node. Or you read some properties, or you remove nodes, or you pick a subtree and put it somewhere else. This is the structure you're working with. But that's not the structure that is displayed to the user. That's a very important fact. Next step, this is only the structure. This doesn't look any good. For the good-looking part, there is CSS. And the CSS is processed similarly. There is a byte stream. This is transformed into characters, into tokens, into nodes, and into the CSS OM, which is another tree structure. And out of the document object and the CSS object model, there is built the render tree. If you're interested in this process in detail, just go to developersgoogle.com and have a look at the web documents. They're explaining this critical rendering path and a lot of other very important concepts in a very good, understandable way. So if you're getting bored at the weekend, just have a look at those documents and have fun with them. Okay, we have our good-looking structure and our structure, and we need to somehow make our document object model look any good in the browser. So the browser or the rendering engine just merges the document object model and the CSS object model and applies the stylings to the structure. Moves some elements somewhere and applies some colors and stuff like that in order to make the web page good looking. The render tree only consists of elements that are visible to the user. So no meta information, no display none elements or somehow hidden elements are contained in the render tree. As soon as you modify something and a node becomes visible or invisible, your browser has to do this work again. So keep that in mind. We're coming on that topic later on. Okay, any questions on that process? That's pretty basic, but very important. You have to understand that there is a whole lot of things to do for our browsers before something is shown to the user. So two tree structures are merged together in another tree structure, which is displayed. How can we increase the performance on that? Okay, first row, any idea? Inline CSS? Yes, damn it. You're correct. Inline CSS is a bit faster than not inline CSS, but think of it. What's about the readability? Maintainability. Think of you in half a year when you put a lot of inline CSS in your application, you won't like yourself. So yes, it increases the speed, but not a good idea.
Could we pre-process the HTML that we send out so that we do the rendering server side one time, like the builds that we do with Node?
Yes, there is a possibility for that, but you're going way too far. So
maybe you would want to keep the tree kind of broad instead of deep?
Yes and no. Just keep the fucking tree small. Obvious solution. You don't have to put a table with 4,000 rows in your page, because the user can't ever process 4,000 rows in the first site. So keep the trees as small as possible. That's the simplest way of increasing the performance. Keep the structures that your browser has to process as small as possible. So deliver a minimal set of HTML and a minimal set of CSS in the first place. After that, you can extend it. You can add CSS, you can add styling, you can add nodes, structures, and so on. That's simple, because the first load is the most important one. Okay, small trees are our friends. So we're going into that bonsai thing. Before you start optimizing things, you have to know where your problem is. A question that I asked in the morning: who knows how to start the developer tools in your browser with a shortcut? Who does not know how to open the dev tools? Fine. Okay. So these are the most important helpers in your daily job. Just learn the shortcut or right-click somewhere and use inspect. That's the same effect. Use them and use them on a daily basis. You can measure everything in your application. So I'm just measuring Google, and they did an amazing job. So do we have a loading problem? This pie chart is phenomenal because it tells me where my problem is. Okay, Google does not have any problem because, no, fine. So here you can have a first idea of where your problem might be. So loading is no problem because 16 milliseconds is just fine. Rendering, fine. 28.1 millisecond, just fine. Painting, even better, 2.3 milliseconds. Okay, remember what the Google start page looks like. There is not that much to paint, so just fine. Other, not that problem. Idle, okay, just fine. Our CPU gets bored. And the main part is scripting. So what does Google do to do that much scripting? They're just measuring stuff. They're just finding out where you are, what you do, who you're talking with, stuff like that. They know you better than you yourself. Okay, but you get a first idea by just looking at this pie chart. When here the rendering piece or the painting piece is big, you know you have to have a look at this section of your page. So this is the first step into optimizing your application. But before we start optimizing our content, the content has to get somewhere to the browser. And the first thing to optimize is downloading stuff. And this is mainly for HTTP1, because HTTP1 does requests for each resource and does this request or does not recycle this request. So you have a certain number of parallel connections, and you can ask your server, please deliver me some HTML, some JavaScript, some CSS. If you're looking at big pages or big applications, there is a large number of requests. And if you exceed that limit here, the requests are blocking each other. So you can process the first 6 or 13 or whatever, then you can process the next and the next and the next, and all the later downloads are just blocked. And your browser won't render a single pixel if there is not the complete HTML or CSS or JavaScript present in your page. So there is a number of workarounds to deal with downloads. How do I fix my performance problem with downloads? Remember the small trees? Keep your files small. Just as simple. How do I... there is a dirty hack to get around this limit. This limit is for subdomains. So you can create a subdomain images.mydomain.something, css.mydomain.something, HTML, and so on, to get around this limit. But that's not the point. You can go around this problem in another way, in a better way. So keep your files small and deliver as few as possible files as possible. So how to reduce your CSS? Use preprocessors. Your browser does not need any comments and white spaces for processing the CSS. So white spaces, such as line breaks or indentation, are just for readability. Your browser does not read your code, it interprets your code. So throw all the unnecessary white spaces away. And there are tools for that. They are called minifiers, and you should use them. The same is true for JavaScript. There is no need for delivering hundreds of JavaScript files. You can put them together. And yes, there is a protocol version 2 of HTTP where the connections are reused, but however, you can just merge them together to fewer, bigger files and deliver them, and then just process them. And your server does not have to deal with server-side push or something. So it's just fine to pack your JavaScript CSS files into one bigger file and deliver them, even with HTTP2. Then JavaScript does not need white spaces or descriptive names for functions or something as CSS. So just minify your JavaScript source code and let the minifier optimize it a little bit. So there is not that much file size to be transferred to the client. And the last one is images. You can use sprites, which packs your images together and resolves them by using some weird CSS magic. There are creators for that, so don't worry. If you have a look at your browser tools, which are opened by some shortcut, you can have a look at the download performance. And you should know of which steps a download consists. There is some connection setup, where the biggest parts are some SSL handshake. You can't nearly get around SSL handshakes because they're providing security, and security costs something. So this is just fine. This green thing here, however, might be a problem, because that tells us we are waiting for something, for some reason, because our server is lazy, our server is blocked, or something. TTFB means time to first byte. So this is the time our browser waits after the SSL handshake to receive the first byte of our response from the server. So if you're optimizing your server, then the green bar shrinks. The blue one means we are downloading the actual content. If your file's too big, then the blue thing here just keeps growing. So now you know where your problems might come from, and you have a slight idea of how to get around it. How can we omit downloads at all? Just put the files to the client. And that's way more simple than you might think, because luckily there is something called Service Worker, and Service Worker, which are not that good supported right now, but even Apple is thinking about supporting them. It took us a long time. So service workers are part of progressive web apps, and progressive web apps means you're writing web applications that run on every system and are increased by features which are not available on all systems, but the application does not break. So these service workers are browser processes which are in fact proxies that are able to intercept requests to the server. So you're going to the server and tell the server, hey, I want to have this JavaScript file, this CSS file, and your service worker is able to intercept that call and answer it directly. You have the ability to store all the files in your browser and then just deliver them from your local hard disk and not from a remote server. And that, in the first line, speeds up your application and is good for offline usage, because if the files are stored offline and you're caching some dynamic values, your application is completely runnable offline. So this is true for the major frameworks such as React, which ships service worker support out of the box, which is true for Angular as well, but they're a little bit late on, and they are just they have slight problems with implementing service workers. They introduced a mobile flag in their CLI component, which didn't work over a long period of time, but they're getting there finally. And we have in all major frameworks this service worker support, which improves the performance of our applications. So what blocks us from showing stuff to our user? If you think of the DOM and the CSS OM, the browser won't display anything if the CSS processing isn't complete. So CSS is render blocking. There won't be anything before CSS is not there, because in the first step it looks shitty and then it will be beautiful, and before the browser displays two versions of your application, it just waits until the final one. So how to improve the CSS performance? Do not use any add import statements. What import does, who knows what import does? Okay, then if you know, then just forget it. Import just references another resource and the browser has to load it, and that's not good for your performance. There are some preprocessors which give you similar features but are able to compact your CSS, put it all together and deliver it in a few or just one file. That's much better. Because if your browser just processes your CSS and stumbles over some add import, then another download is requested, and the processor waits until the response is there and then just continues to build up the CSS OM. So no good idea. Use as less CSS as possible, so keep the tree small. And the helper in this place is the media attribute. With this media attribute, you can flag some style sheets that they're just processed for a certain condition. So if you imagine a mobile website, you can put a media attribute in your source code, and that tells the browser, use this style only for the mobile version, use that style only for the desktop version, and the desktop version style sheet is not processed for the smaller resolution of my mobile phone, and that just keeps the style sheet small, and that just keeps the CSS object model small, which is good for our performance. And here you see the absolutely last resort solution is inline CSS, because that's absolutely no good idea for readability or maintainability or for your future self. I know what I'm talking of. So the same is true for JavaScript. In the dark old ages, you used inline JavaScript. And you had the problem, if you put the script tag in the top of your page, you cannot access stuff that's behind that script tag. And the simple fact of that is because the browser runs through the HTML code, finds the script tag, executes the script, then processes the DOM further. So it's not a good idea to put a lot of JavaScript in the head of your page, because that blocks rendering. Not a good idea, because no single pixel is shown. And you can do whatever you want in that top JavaScript section. You can, for example, talk to your server and load some stuff and things like that. But in the meantime, nothing is shown to the user. So a better solution for that problem is asynchronously generating script tags, which are inserted later on, using the async or defer attributes, which delay the processing of JavaScript, or use a loader such as Webpack and a grown-up framework such as React or Angular, which support lazy loading. And with that feature, you can tell your framework, I need this and that component just later on, and process it when it's used. Google introduced architecture, which is known as the app shell architecture, which is simply the frame of an application with static content, and that loads fast, displays the user something to interact with, that could be cached, and all the dynamic content will be put in that application frame. So you can deliver something very quick which catches the eye of your user, and your user is just caught by your fancy application, and then you put the rest of your application into that shell. So your users see that there is something going on, have the information, and know, okay, there will be some more stuff and I have something to do and I won't get bored. That's the most important thing. So all of the stuff we just talked about was true for nearly every web page. There's a special type of application which is a single page web application, and that means that your user don't change pages while using the application, but stays on one page, and the page is modified throughout the life cycle of your application. That means that there are no page loads, so no Control R or F5 or something, and there is no chain, no side effect full change of the URL line, and the state of your application is stored in the memory. If you hit F5, then the page is refreshed and the state of your application is gone, which is not a good idea in a single-page web application. All the objects of your applications are stored as well in the memory, and the not so good side effect is that the memory consumption of your application increases over time. We had the fact that our users are using our web application, which is pretty good, but the browser consumed 4 to 8 gigabytes of memory in the evening. So our users were forced to reload the browser in the evening because in any other case, the browsers just won't work in the morning. So how did we get around this problem? Simply by knowing what's under the hood. And we talked about HTML and CSS, and now we're on JavaScript Engines, so the heart of our browser when it comes to JavaScript. And the lucky thing is, for us, that there are competitors on the market. So there are a couple of companies which do browsers. Some do it better and some not. And one of these browsers here is not existent anymore, luckily. And so Chrome, Firefox, Edge, and Safari are nearly head-to-head when it comes to performance, features in the meanwhile. So they're pretty good things to work with. We're just having a look at one of these engines, and guess which one? The Google one. And this is for 2 reasons, because it's the market leader and the engine is shared between the Chrome browser and Node.js. So everything I'm going to tell you in the next couple of minutes applies to Chrome in the browser client side and Node.js on the server side, and that's pretty handy. So the first optimization of your JavaScript engine is hidden classes. And I hope you remember the example with the array and the caching stuff at the beginning. So this 1.7 milliseconds compared to 0.0 millisecond stuff. And here is the explanation why the performance increased in that level. Because if you're working with JavaScript, you're working a lot with objects. Everything is an object. Even functions are objects. And you're accessing properties all the time if you're working with JavaScript. So the browser manufacturers just recognized we have to do something about this. So they keep a big dictionary of where the properties are stored in the memory, which is good, but not for 4 to 8 gigabyte of JavaScript objects. So the V8 engine maintains a smaller dictionary per object where to locate the single properties in the memory. And this is called a hidden class. So we're just having a look at a typical JavaScript class. This is a class underneath the hood. JavaScript classes are transformed to constructor functions and prototypes and all that stuff. And if you're working with a point class, which you can write class point, constructor, X and Y, and stuff like that. So that's just similar. And then you can access properties. And what your engine does, if you're calling the new operator on the point class, it generates a hidden class. This is the basic construct. You have an object and you have a corresponding hidden class. Then you go to the next line and access the X property. Then another hidden class is generated, and it knows where to find the X property. Then you go up to the next line and you have another hidden class which knows where to find the X and the Y, and you have a transition from hidden class 0 to hidden class 1 to hidden class 2. So if you have another point object, P2, which is generated by the same constructor function, then the same transitions and the same hidden classes are used. So for the first access, this thing is terribly slow. But for every other property access, this is blazing fast. So it's good to use JavaScript classes, because then you ensure the same transition and the same usage of hidden classes. And it's fast. Any questions on that? Fine. So remember, reuse things and use classes. That's a good thing. Don't introduce any additional properties. Just use them in the constructor, declare them, and then they are used always in the same order. Because if you mix up the order, then the transition is not the same and the performance is gone. The next thing is the just-in-time compiler. JavaScript is not... Yes, because a static class is just another type of object, and it applies to static classes as well. It applies to everything in JavaScript because everything is an object, and all the objects share just the same inner structure. So JavaScript is not processed as plain text because that would be also terribly slow. So JavaScript is compiled to machine code, and that's why you have to, if you have a change in your source code, you have to reload it in the browser or reload even your node process, because JavaScript compiles your code in machine code, keeps that in memory, and does not know of any changes in the files. The reason for that step is because machine code can be processed much faster than plain text, and the engine can optimize the code. So this is an example from the V8 documentation, and the machine code looks in that way that the engine just patches the hidden classes and just tries to use the hidden class which was patched in, and if the hidden class is correct, then everything's fine and everything's high performant. If not, then the engine detects the miss of the memory, or the cache miss, and it goes back, reverts the optimization, and falls back to the original machine code version of your object, and the performance goes down. So please reuse your structures, because that's good for your performance. So as I said, everything's an object and everything's in memory. So one important thing is the garbage collection. Garbage collection means there are things in the memory which can be used, and if you do not use them anymore, the memory has to be freed. And what means unused objects in the memory? There are no more references to your objects in the memory. A reference is simply a variable pointing to something in the memory. If the variable is gone, then the reference is gone, then no one can access the object in the memory, and the garbage collector can throw it away. So how can you delete variables? With the delete operator, by leaving your current scope. Yeah, and that's basically it. So leaving the scope, if you're in a function, and introduce a variable with var or let or const, and then leaving the function, the memory is freed by your garbage collector. And that's pretty good. What's also good is that the V8 engine puts the memory management in the idle time of your processor and does not block any CPU resources which is needed for processing JavaScript. So that's a further optimization which ensures, for example, fluid animations. So basically your memory is divided into two sections, a young generation and an old generation section. And if you're working with JavaScript, you're generating objects. And these objects are stored in segments of your memory. And as soon as one of those segments is getting full, all the objects which are currently in use are moved to the next section, and all the other objects are thrown away because the memory section, the older memory section, is just swiped. So this algorithm is very fast, but memory consuming. And that's just for short-living objects, because if you move an object for the second time, it gets moved to the green section, the old generation section, and this is the section where the older objects live. It's something of a retirement area, but yeah, no, just kidding. The green area is has another algorithm, which is not that memory consuming, because you know that 4 to 8 gigabyte, which would be pointless with the yellow one, but this one has an algorithm which is known as mark and sweep. All the objects which are currently in use are marked, and all objects without a mark are just deleted. And that's time-consuming, but memory-friendly. Time-consuming means a complete run can take up to 100 milliseconds, and this bigger garbage collection cycle happens just over time. But the engine just tries to split it up into smaller chunks, which take up to 5 milliseconds, which is just fine. So try to move as few objects as possible. How do you move as few objects as possible? Reuse your stuff. That's the main thing. Reuse structures, reuse objects, and then you're just fine. JavaScript is intended to reuse stuff, so a lot of optimizations are just getting active if you have a longer running application. If you have a page which is visited for 5 to 10 seconds, nearly none of those optimizations are just activated. So for single page applications, you can rely on the stuff I just told you. For throwaway pages, you don't have to deal with it, because you stay there for a couple of seconds and then just go to the next page. You don't have to deal with memory consumption and stuff like that, because it simply won't happen. What will happen is repaints and reflows. And now we're leaving JavaScript for a while, because we're just going back to the trees. And this is what the browser does when you're working with an application. So a repaint is the process that the browser checks every element for its visual properties. So you remember the render tree? If you modify it somehow, or you fiddle around with your DOM and an object gets displayed, then your browser suddenly has to do some work, because the DOM needs to be recreated, the CSS object model maybe needs to be recreated, and the render tree needs to be modified and recreated. And that's kind of work your browser has to do in regular intervals. So checking for visual properties is one thing, and a reflow is the recalculation of the layout. So the position and the measurements of your containers or the DOM elements. And every reflow triggers a repaint, and that's responsible for redrawing your page. How can you start a thing like a reflow? And that's quite easy. Just start scrolling and your browser is activated and recalculates the layout and repaints with every scroll event. Change the window size and the process is kicked off. Addition or fiddling around with elements, style sheets, classes and stuff like that, that's just obvious. What's not so obvious is this one here. Reading measurements. If you're going to a div container and ask it, how high are you? I'm very high. Then it tells you I'm 50 pixel high and it triggers a reflow. And that's just bad for your performance. So there are a couple of things you should do. So in order to omit the reading of variables or of properties, just cache the stuff in your JavaScript. That's easy. Omit single style changes. So don't change the height, the width, and the color of an element, but change it all at once. How do you do that? Use CSS classes where possible, because then you apply a group of changes all at once. If that's not possible, there is a better solution than just cascading the changes, but remove your elements from the visible part of your page. Just detach it, jQuery detach, for example. Change the element, so the subtree of your DOM, and then the changed subtree is appended to the DOM or attached to the DOM again, and you have only two layout changes, which is the removal of the subtree and the attachment of the subtree, and not every single change. Yeah, and the last thing is use fixed positions for animations, because that's good for performance. Rendering is reflow. Painting is repaint. And if you watch the performance of your application over time, you can see what your browser is doing here. And if you see a lot of rendering and painting events, you know that there is something happening. And maybe that's intended because the user scrolls like something, or it's not intended, and then you have to become active and change your source code. That's a great topic, because if you're running into a kind of that problem, it's not funny. Because to find a memory leak in a big application can be hell. A memory leak slows down your application or your whole system, because your browser just consumes all of the free memory of your application, of the system. If the memory consumption is high enough, the browser or the whole system crashes, and the whole behavior of your system gets not that good. When do memory leaks occur? Simply when the garbage collector is not able to free memory. And that's easy, because if you're using global variables, you have always a reference on that piece of memory, and it gets not freed. So if you have the idea of caching all the stuff in a global variable, it's not the best idea you have. If you somehow forget intervals, which happens from time to time, it's consuming memory, because intervals just trigger functions, and functions have a feature called closures. And a closure is a function, and it's creating context. And that means a function has access to itself, so this unused thing, but also to the creating context, which is the context that lies around. So you can access this thing here, and as long as this function exists, the complete context is available as well. So this little script here just causes the perfect memory leak because it just fills up your memory. And just imagine this code is a plain memory leak I presented you here. And this code can be located somewhere in your application. And to find this is hell. It's not fun because you have a lot of objects in your browser memory, you have stuff going on, and then just find tiny little pieces which sum up in your memory is not that easy. So everyone who ever has analyzed a memory dump in the browser knows what I'm talking of. So not funny. Okay, so far to the horror stories. Better topic, animations. We're getting fancy again. So why do we want to do animations? Because we can point our users somewhere and we can make the usage of our applications much more easy. And for that, we can use animations. So the simplest way of animating things is to periodically change CSS properties, and then suddenly your div containers begin to rotate or something. That's not the best idea, because if you change CSS properties manually with JavaScript, it runs on the CPU, which is not good for the performance. The garbage collector further slows down the whole process, and you don't have any fluid animations, but it just looks crappy. A better alternative is the Web Animations API, with which you can control your animations, but it's not that good supported right now. So as far as I remember, Safari and Edge do not support the Web Animations API yet, but they will in the near future, I hope. And until that, just use CSS animations. CSS animations run on the GPU, are fluid, and your browser is able to optimize them. And if that's not enough, then just don't use transitions, which animate properties in a nice kind of way, but use keyframe animations, which provide you a very good way of controlling animations. You can control every single piece of an animation, but it's hell to write by hand. And then just go for generators such as CSS Animate or stuff like that, and then you can drag pieces around and animate them this way. So the last thing I want to show you is how do the others do performance? And that's just simple, because they're talking a lot of performance improvements and what they did. A good example is Facebook with their framework or library React. They just rewrote the whole core of the library in order to get a better performance and be able to include future improvements. So React has a feature which is named the virtual DOM, which abstracts the slower DOM. So you know every DOM manipulation is slow. And Facebook just realized that and put an abstraction layer in that. Abstraction is not only the best thing to do, but in this case it is a good idea, because they calculate all the operations needed to transform the application state from A to B and optimize the change in a way that is performed in an optimal way. So the transition from state A to B is just optimized for you. And you don't have to deal with it, but only to describe the new state of your application, and your library handles the rest for you. With that rewrite, there comes another feature which is known as scheduler, and you have different schedulers for different kind of updates in your application. So if you, for example, have an animation which is real-time and should be very fluid, then the real-time scheduler works and just animates in a fluent way. Then your application gets an update by calling the server via AJAX and getting back a certain amount of data, and this data needs to be displayed. It's not relevant if you display it in second 1 or in second 1.5, because the server call just takes you 2 seconds or something. So a couple of milliseconds don't matter, but for the fluid animation, it matters. So first, the animation is ended in a controlled way, and then the update from the server is displayed. So you have the fluid animation and you have the display of the server information, and everything's just fine. So they're investing a lot of money in performance in order to keep Facebook.com performant, but you can use this framework as well and get the same performance. So win for every page. Any questions?
This JavaScript animation versus CSS animation, there are a lot of things that GSAP is doing that is displaying how much faster GSAP is compared to CSS animation, with the timelines and everything.
Yes.
So that's why I was wondering why CSS animation should be faster than JavaScript animation.
CSS animations is optimized in the GPU, and the Web Animations API is not supported by all browsers. Yeah, but you cannot use it in Safari, for example. So if you're doing a mobile web application and you have customers with an iPhone, you're simply lost. I'm sure they have a fallback, but with CSS animations, you have very little control over your animation. So if you want to stop the animation with JavaScript, you have to deal somehow with that. And that's not an easy task with CSS animation. So if you have the chance to go for the Web Animation API, you should do. That's the simple fact. Any further questions? Have you ever written a keyframe animation? Yes. That's hell. So if you have the chance to use a transition, use it, because it's much less to write. That's the simple difference. Any further questions? Okay, then thanks a lot for listening, and hopefully see you tomorrow.